Hi, my name is Andy Keeton, and my project is an analysis of the negative feedback and a proposal of transport protein system in the enzymatic hydrolysis of cellulose. So a little background to this project. There's been a problem over the last couple of decades of an increase in anthropogenic CO2 into the atmosphere. This has mainly been caused by increased use in fossil fuels. So the solution is using a different type of fuel. One possible example would be bioethanol. If you look at the emissions here, you see that fossil fuel has an emission of nearly 85, whereas cellulosic bioethanol, which is the type that we're going to be looking at, is down near 0. So let's talk about the bioethanol production process. It's a three-step process consisting of the pre-treatment of cellulosic biomass, the enzymatic hydrolysis of that pre-treated biomass, and fermentation. The slowest and rate-limiting step is the enzymatic hydrolysis. So that's the one that needs the most improvement in order to improve the entire process, and that's the step we will be focusing on in the rest of this presentation. So let's look at that step. Cellulase is a cocktail of 3 different enzymes: endoglucanase, exoglucanase, and beta-glucosidase. We'll be focusing on exoglucanase and beta-glucosidase. Specifically within exoglucanase, we'll be focusing on cellobiohydrolase, which is an enzyme that breaks down short-chain cellulose into a dimer of glucose called cellobiose. The cellobiose is then broken down to 2 glucose monomers by the enzyme beta-glucosidase. Now there's another aspect to this as well, as cellobiose and glucose both work to negatively inhibit their own production by binding to cellobiohydrolase and beta-glucosidase. However, to look at how the system would work without the negative feedback, we're going to look at just the positive control system. As you can see here, we have E2, which is cellobiohydrolase, breaking down cellulose, CI, through the use of an intermediate to form cellobiose, G2. Cellobiose is then broken down even further by E1, which is beta-glucosidase, through another intermediate to form G1, which is glucose. So the system was simulated in MATLAB using the biosystem code. First, the constants were added, and their values were taken from literature. Next, the compositors were added, and their initial values, also taken from literature, were added as well. It was assumed that cellobiose and glucose, along with the 2 intermediates, had an initial concentration of 0 milligrams per milliliter. Next, rates were determined for each of the reactions in the previous slide. These were added to part 1, the positive control system, in the code. This part was then added to the system and was simulated over various time intervals until an appropriate time interval of 500 was determined. Next, the compositors were plotted. Here's an example of how one of those plots was made. This is the plot of CI and G1 versus time. So here are those 3 plots that came from that simulation. The first one on the far left shows CI and G1 versus time. The next one shows the enzymes. And the final one on the far right shows the intermediates in the process. Next, we introduced the negative feedback that I talked about a few slides ago back into the system. Now, the negative feedback is due to both cellobiose and glucose, like I said. And this first slide shows you the negative feedback due to cellobiose. Now, cellobiose can bind to the active and non-active sites of cellobiohydrolase, which is shown in these 3 reactions. Here's the negative feedback due to glucose. Glucose can also bind to the active and non-active sites of the enzymes, yet it can bind to both cellobiohydrolase and to beta-glucosidase. So 6 reactions come from the glucose negative feedback. In total, we have 9 reactions from negative feedback in the system. The negative feedback system was then simulated in the same manner that was done with the positive control system. The same 3 plots were produced, the one on the far left being cellulose and glucose, the one in the middle being the 2 enzymes, and the one on the right being the dynamics of the intermediates. A comparison was made between the positive control system on the left and the negative feedback system on the right. As you can see, there's a pretty significant decrease in final glucose concentration on the right plot. On the left, we have a 7.97 milligram per milliliter final concentration of glucose. Yet on the right, with the negative feedback, it's only 6.709 milligrams per milliliter. That's over a 15% decrease. Yet, if you look at cellulose, the concentration with the negative feedback is only about 0.5 milligrams per milliliter, which doesn't account for the big difference. Therefore, it can be assumed that the glucose is trapped somewhere else in a different compound in the system. So we looked at the intermediates. The intermediates showed that the assumption was correct and that glucose could be found in other forms, yet even here the final concentrations only total about 0.04 milligrams per milliliter, which still does not account for the difference. When you look at the comparison of E2 and E1, however, you notice that E2 and E1 have very, very low final concentrations when the negative feedback is introduced into the system, versus on the left where you have just the positive control system. Therefore, it is inferred that the two enzymes are found in not their free but bound state in the negative feedback system. The negative feedback dynamics were then plotted to determine at what state these enzymes were found in. As you can see, the two plots on the right show glucose being bound to the two enzymes with very high concentration, yet the one on the left shows that cellobiose binds to the enzyme cellobiohydrolase with a fairly low concentration. Therefore, we're going to ignore the plot on the left and we're going to focus more on the two plots on the right. Next, we looked at what specific species of compositor we have where the most effect has been done by the negative feedback due to glucose. In the second one, it can be seen in the blue line, which is E2G1. And in the third one, it can be seen in the blue line as well, which is E1G1. So what should we do? Well, we have to reduce or eliminate the formation of those two complexes, E2G1 and E1G1. This can be done by either removing E1 and E2, or simply just G1 from the system. So we decided to introduce a transport protein system that would bind to G1 immediately after its formation and transport it to a new cell, therefore not letting it bind to E1 or E2 and form those complexes. Here's the reaction scheme for that process. As you can see, glucose is first bound by a new enzyme, E3. It's important to note that the affinity it has to binding to E3 must be much higher than the affinity it has to binding to E1 and E2. Next, the enzyme glucose complex is bound by a new protein introduced into the system. This can then degrade to form free glucose in the cell, but in order to make sure that does not happen, you have the protein transport the enzyme glucose protein complex to a new cell. And it's important to note here as well that Kt must be greater than Kdf, which is the dissociation constant. That way, the majority of the glucose can leave the cell and is not replaced as free unbound glucose in the original cell. Once in the new cell, the glucose can then dissociate from the complex and then bind to a new enzyme, E4, which would then begin the process of fermentation. The constants were given arbitrary values that made the system work as efficiently as possible. Next, the negative feedback was plotted similarly to how the negative feedback system was plotted. As you can see, there's very little negative feedback due to the transport protein system. In fact, at time t equals 500, every compositor is at nearly 0. So then finally, the dynamics were plotted to see if it matched up with the positive control system. As you can see from the middle and furthest right plots, those plots look very similar to that of the positive control system, which is a good sign. When you investigate the furthest left plot, which is that of looking at the concentration of glucose and cellulose over time, you see that the final concentration of glucose in its bound form to E4 in the new cell is at 7.967 milligrams per milliliter. This indicated only a 0.04% decrease from the final concentration of glucose in the positive control system. Therefore, the transport protein system works very well to overcome the negative feedback in the system. So in conclusion, the most impact from the negative feedback came from the formation of the E2G1 and E1G1 complexes. So to make the process more efficient overall, the formation of these processes needs to be reduced or eliminated. In order to do that, a transport protein system was introduced that removed G1 immediately after formation, making it so that it could not form those complexes anymore. Now, when the binding affinity to the new enzyme was much greater than the binding affinity to the previous two enzymes, and the Kt was much greater than the Kdf, the negative feedback was almost completely eliminated, showing that the transport protein system was a good way to overcome negative feedback. Thank you, and here are my citations.